So, as Ben said, I've worked on a bunch of fairly large-scale projects in the last few years. So, to answer the question behind this spooky picture, who am I? I was one of the originators of EC2. I'm going to tell the story that there's an origin myth to EC2. Lots of folks are wondering how it started. Lots of folks think they know how it started. I'm going to tell a story that may be a little different than what you've heard before. My story is my story true? As true as any of the stories can be. You get to decide. So I also worked on what was called the Edge Computing Network at Microsoft. If you've seen the Microsoft Azure CDN or some of the distributed compute that they're doing now, that was our effort. Originally built for internal consumption. Lots and lots of traffic. If you've seen things like Windows Update or some of that, that comes out of the CDN that we built as part of the project. And now, VP Engineering at Oxford. So I was really happy to see the number of people who are using Chef. Let's see the hands. How many people like Chef as opposed to just using it? Same number of hands? Because I know Archer Berkman yesterday told me, every time I use Chef, I want to hurt you. Okay. Not everybody loves it. All right. So, why are we talking about this? Why is this germane to search? So the big guys, Google, Amazon, Microsoft, they all build their own tools, right? They're big enough to have dedicated teams to solve the big problems, right? What do the rest of us do? Yeah. Almost everyone else is forced to either use something that's off the shelf that doesn't quite fit your needs, or build something and kick it to fit. One of the things I thought was really impressive is I went to Gears Talk, and he talked about the architecture that they had and how far they pushed Rails, and he reached this point. I'm like, wow, that's not evolution, that's revolution. We can't push the architecture any further. If you're lucky like those guys are with the run rate they've got, you've got the money to spend to build the new thing. But you all reach that point, right? It's like, okay, do I build something? Do I fail in place? Do I just watch the site melt down? What do I do? So most folks are actually unprepared for success. So I'm going to give an overview of some of the things that I've learned building some of these services that hopefully put you on the right path, things that you can compose and use as you get bigger and bigger. So today, there's a lot of confusion out there. Everybody wants to build, everybody wants to succeed. First step, bootstrapping. Wow. Okay, a lot of options. Look at this list and ask yourself, how many of these options were available 3 years ago or 5 years ago? Right? Most of this stuff pretty new. So some of them have been around a little longer. It's an evolution, but these are early days. Look at this. Look at how much it's changed. But now, with all of these choices, what do you do? Right? It's already confusing. Who do you go with? Who do you bet on? Who's going to be in business next year? After bootstrapping, configuration. So this is where we come in. So you've got VCF2, CF Engine. How many of you have used CF Engine in the past? Yeah. Okay, one more. How many of you went from CF Engine to Chef? See, it's a weird transition. Some people stay on the CF Engine forever. Lots is the backbone of the last, 10 years? And then finally, command and control. So you've got to do something. Now, not a lot going on at this level, right? So you see the progression. A few years ago, we figured out that we need, infrastructure as a service. We can bootstrap. We're moving up the stack just a little bit. Now we're doing configuration. Now we know we need more orchestration. So we're building these layers up and up. And the common theme here is that we're trying to build something that is generally mass consumable. All those folks out there who aren't as big as Google or Amazon or Microsoft, they need solutions, and wouldn't it be great if you could start composing these out of the box, right? You don't have to build your own thing. So, got it? Who likes the definition of the cloud? What is the cloud? Is it all of that stuff that I was just showing? Does anybody know what it actually is? Let's go back to the beginning. So I mentioned there's an origin myth to EC2. Now, a few people may know something really fast. Who knows where EC2 started? Who doesn't know me personally and knows where EC2 started? Stop that in the back. How about continent-wise? Which continent did it start on? Africa. There we go. Strangely enough, first 2 years of EC2, all core development happened in Cape Town, South Africa. So the story is, this guy, Chris Pinkham, was my boss at the time. Chris is from South Africa. Chris, by the way, is also the co-founder of Nimbula, another one of the recent private cloud companies. So yet again, you're seeing it, more progression out there, more building in the cloud. Chris was VP of Infrastructure at Amazon, and along with our very own Ben Black, started talking about more dynamic, more flexible infrastructure. As a matter of fact, as far as I know, Ben was the one that wrote the first paper of what eventually became EC2. So Ben was there at the very beginning. As a matter of fact, Ben's the reason I went to Amazon. So he had a lot to do with this. So there was this paper passed around, there were meetings with senior VPs, eventually with Jeff Bezos, and then Chris Pinkham decided that he was going to leave. He wanted to move his family home to South Africa. Well, his boss at the time, Rick Dalzell, fabulous, fabulous senior leader, said, well, why don't you start a remote development center there? Wow, South Africa. So Chris is moving home. One day I was having lunch with him, I said, wow, man, that's fabulous, I'm jealous. At some point I'd like to do the same thing. Just deadpan looks over the table at me and says, how would you like to staff a team for me? Ah, okay. So I packed up my family, my wife and 2 kids, and moved to Cape Town. And from there we just started hiring like mad. So within the space of 2 years, we had that first view, the thing that people started using originally for EC2, about 15 people. I interviewed, I think, 14 of the first 15, and that was it for the original product team. So when you think about it, that's not a huge number of people for something that eventually, ended up being fairly well known. So why did we do it? The second part of the origin myth is, wow, it was all about excess capacity. Amazon's got all these machines that they only use over the holidays. Amazon's usage pattern, as you probably saw in Gears Talk, doesn't look like the Guild Group. It's not like Amazon peaks at one point during the day and goes away. Amazon's running a lot of traffic all the time, and Amazon is smart about capacity planning. They don't like to have a lot of excess, and it wasn't just laying around for us. So that idea that we just took those extra machines we weren't using in the fourth quarter, no. We had to fight tooth and nail with some of the other brand new groups. Like I fought with S3 over the first few racks. They had these racks coming in, and we wanted them, and we eventually got a few brand new, shiny racks. The first payment to Aaron for our first AS, our autonomous system, went on my personal credit card. So it was kind of a weird time. So, what is this dynamism? Why did we bother to do this? So, one of the first things we learned is it was really hard for developers to get at something they could experiment with. How many of you have a test environment for your developers? How many of you have more than one test environment, or the ability to spin up a test environment for any dev or any project that needs one? Yeah, fewer hands. This is what we were going for. We were going for the ability to just grab what you need at the time and then give it back. Because we found that most of the projects never got out of the gate because there was someone that said, you can't spend that much money. And what are you going to do with the machines? And so the flip side of that is you get hoarded. Wow, I get to buy 50 machines and I'm keeping them forever. And then the budget goes away and nobody else gets a machine. So isolation. Obviously, if you want people to play together in the sandbox, you need some way to keep them apart. The cat moves over there, the kid plays over there. And then utilization. Amazon was really good at spending the right amount of money. And so there was a lot of discussion, well, how much does it cost? What is the dollar per unit of compute, and how do you use that? So all of these things came together. And out of this wasn't a plan to just build something for use internally. As soon as we came to a number of these conclusions, it was actually, wow, we could probably sell this to people. And so even from the very beginning, the notion was, we're going to build a new service to sell. S3 was just launching. So we have this storage service. What if we had an execution service? And so for about the first year internally, that's what it was called. And then somebody finally explained to us that that didn't sound very nice. How would you like your applications run by the Amazon execution service? Not like EC2 was a lot better, but yeah, so I get it. So these are the things, when you run on EC2, that you're actually paying for, right? The next thing we realized, most applications not that big, especially in the beginning, right? So all of these folks who want to experiment, folks in the outside world, so outside of Amazon, outside the big companies, folks who want to build brand new applications, where do you go to do it? You know, two guys in a college dorm, well, look at some of the success stories. Guys who came out of colleges with brand new startup ideas typically wrangled and stole machines inside the college first, right? Whatever was laying around. It's hard to get your hands on enough gear and hooked up to enough bandwidth to actually put something out in the world. And then what happens if you're successful? So you've got your 3 machines, you know, back in the day, 3 machines, and maybe you got a T1. And then what do you do when you get big? You probably don't have enough cash yet to build out a whole data center, but you're going to fail if you don't start to scale. So if you're not that big in the beginning, you need something that scales with you. Pay as you go, on-demand resources. So we realized, you know, LAMP actually scales pretty well if you push it hard, right? If you do the right things, if you learn as you grow. So these are old numbers now, but the notion is, at the bare essentials, don't design for 1 million users. Build the thing that is successful today on the amount of hardware you need today, and then keep planning, and keep iterating, and keep growing. And with something like EC2, you can keep consuming. Now, I don't know about you guys, now that I've left Amazon and I'm at a startup, we've got a really big AWS bill. How many other people in the room have really big AWS bills? Yeah, see what I mean? When you think about it, it's not a bad business. After all, there's a margin in there. But that's the thing, so don't design for 1 million, just keep iterating. And what's really important, if you've got the ability to experiment, if you've got the ability to throw an instance away and get a new one, or throw an instance away and get a bigger one, ship early. You know, ship all the time. Keep iterating. You know, it may be ugly, but tomorrow it'll be better. So this notion of continuous deployment, everything's always getting better. Ship ugly. You know, at least you're shipping. Customers will like it. Tomorrow it'll be prettier. Customers will like it better. You don't have to wait for these 6-week procurement cycles. Stand up a few more instances, run the application, keep iterating. So, finally, just a small bit of comparison. One of the reasons, like I said, we built this thing is that we wanted the little guy to have a chance. Look at the way the big guy does it. You know, I worked at Microsoft not that long ago, and seriously, rolling in 10,000 servers a month. They were doing data center designs that were set up just to bring new containers in. You know, you hook up connectivity and cooling, slide another trailer in, run it for its lifetime, slide it out, slide in a new one. Very few companies have those resources. How are you going to compete with something like that, at that level of granularity? Alright, is that text legible for everyone? Cool, I was a little afraid this packs a bit too much on the slide with this contrasting. So, when we started to build it, what were the things that we were thinking about? And this is where it becomes germane to other folks who are building applications. We wanted to minimize the management footprint. Now, if you run virtualization on your own, you know that you're taking some resources from the box for everything you do behind the scenes from your customer. So we had a budget. We were always trying to track exactly how much are we going to run in the DOM 0 for a Zen-based system. What can we get away with? Right? So we flipped that over and said, okay, well, if we're going to take it out of the management overhead, what can we run in VMs that look just like customer VMs? I mean, it was a constant point of contention. I thought it was great. This is one of the things that Chris Paton pushed hard on us all the time. Why does it have to run in DOM 0? Why is that privileged? What happens if it's exploited? What happens if you simply run it in a VM just like the rest of the customers? And it's a great analysis because you come to find that there's very little that you can't do just in the VM. Obviously, there is some management stuff that we do in DOM 0. It's a great way to look at it. You know, run like the customer, because then you experience the variability of networking like the customers do. You know, experience all the other problems of having noisy neighbors. It's just a great design for them. Forced to analyze what runs the privileged space. Corollary to that, you harden everything. You have to be worried about security, you have to be worried about, you know, the reliability and availability if you're running just like everybody else. And if you do that, it implies that the service gets better for everyone. And it's an analog to eat your own dog food, right? If your instances are running badly, chances are they're running badly for customers too. So true multi-tenancy, I don't know if we were the first to do it, but might have been, to really run customers, competing customers, perhaps side by side, with hopefully very little concern as to whether or not there's, you know, porous walls, so the data, you know, one customer's data doesn't show up with another customer. How many people actually trust AWS to keep their data secure and to keep their data out of other customers' view? Yeah, not completely convinced. That's interesting. Even to this day, there's still a question about that. How many of you are concerned about things like PCI compliance or HIPAA regulations or, I think you're seeing these private clouds or secure clouds. I think that's going to be that next wave that crests and confuses people. And then finally, I really enjoy the last part. This is designed by Fight Club. You are not unique. Nothing you do is unique. You ought to plan for instances going away. You can't coddle them and nurture them like you do real boxes with real essays. You ought to just plan for it to fail and bring up another one. Because on a large enough timeline, the survival rate drops to 0. How many of you have just lost instances on EC2? There we go. Okay, correlate that with how many of you have high AWS builds? And liking it? That was a little too flippant, wasn't it? Sorry. Yeah, I've noticed that at work very much. I can say that. The other thing is, I'm not sure other companies use other terms, but one of the things that we circled back and forth on constantly is this notion of primitives in design, this notion that you've got an API that does one simple thing and does it very well and does it with a minimum of policy. A lot of great examples in the world today are Dynamism, DNS with an API, fabulous. So you've got infrastructure, compute capacity with an API, DNS with an API, storage with an API, all simple and composable. And why would you want to do it that way? Because you can't, as a provider, you can't outthink the customer. The more policy you put in, the more platform you build up, the more you win on the decision-making process. Well, I think all of the customers are going to do it this way. You're going to be wrong, and you're going to narrow the field of opportunity. You're going to narrow the ability for your customers to build an ecosystem. So if you make it with these primitives and you let the customers compose these, customers will surprise you. Another example of this is with UI versus API. Always build the API first. If you build the UI first, almost guaranteed you will build policy into the UI. You'll have logic there, and if you try to go back and build the API, customers will be confused because it won't act quite the same way. But if you compose and you build your UI on top of your own APIs, everyone is consistent, everyone sees the same things. You also discover the design flaws in your APIs if you do it that way. If you can't use it, your customers can't use it. Believe me, this is a great point of feedback on Chef, OpsCode's current product. We get this all the time. So we're learning and we're reinvesting as well. I think I just covered this. If you do make these simple APIs and you make it composable and you give people the green field, what happens? They start building things you didn't expect and at a rate that is just amazing. So one weekend to prototype a new app, to put it on the web, and then the ability to scale it as you build the architecture. 5 years ago, how could you have done this? Where would you have done it? If you were a brand new application builder, would you have had access to the APIs to even do a mashup like that? Probably not. Another guiding principle, simplify. Simplify everything. What you want to do with those primitives, the lowest level, the most granular things you've got, you want to make those simple, keep them very easy to understand, and move the complexity up the stack. Even inside of your own design, as you're composing, move that up. So it allows you to recompose, to build things differently, and to reason about those smallest components, so it's easier to debug your system. So good examples of this are in networking. So how many of you have complex networking configurations at the switch level? Say at the top of rack switch. Anybody? Typically that's not where you put the complexity, right? So we'll talk about that along with failure domains in a moment, because the two overlap. Where you put your complexity determines the size of your failure domain and your ability to react to that when it fails. And also, simple and open tend to win. The easier the API is, the more approachable it is, the more flexible it is, the more likely it is to win. Examples here about OAuth and OpenID. One from my experience that I'm actually really happy with is the EC2 metadata. How many of you on EC2 actually use the metadata exposed to your instances? Okay, a few. We had lots of discussions as to how best to expose that inside of the customer VM. And so for folks who don't know, we expose it over HTTP. So they're really simple REST-like endpoints where all of the metadata about your instances live. What is my instance ID? What is my reservation group ID? IP address, things like that. Things that are really simple and germane to your configuration, Plus you can put user data at launch, arbitrary user data, into that structured query. We expose it inside the instances as HTTP. Every instance thinks it sees the exact same address, but if they go to that address, they only get their own metadata. So what does that allow you to do? Any unique instance that comes up can perform exactly the same action as any other, but get the right data, protected from all the other users. Now, HTTP, simple and open, you can use curl, you can write a bash script at startup to query against this. Now compare that to some of the alternatives. We could have done file injection. Now you got a problem. So, which file systems are going to be there? Which OSs support that? How do you know where it's going to be? How do you know where the customer wants it to be? What do you do when it's an OS where you know how to copy over this kind of file system, but not this one? What happens in the boot sequence if the customer is allowed to make that file system read-only before you get a chance to copy data? There are all these decisions to be made, and we couldn't predict ahead of time customer policy, but we can make it really easy for you to query out. In HTTP, like I said, everybody knows that. Simple. All right, I'm going to bring the rest of this one up quickly. This has actually come up in a number of conversations with folks here. So, is the cloud cheaper? What's the answer? No. There we go, yeah. Depends, or no, with a side order, it depends. The cloud, as I said earlier, what you're really getting out of it is dynamism, right? This ability to get new instances if you want. That's what you're paying for. If you're treating it like standard static hosting, it's not going to be cheaper. It's not meant to be. Those things actually don't compare. So when you see some of the comparisons out there in the literature, you're looking at the wrong thing. What it is capital expenditure versus operational expenditure. You know, you're not buying your own servers, you're not amortizing that, you're not depreciating that over some curve. What you're doing is you're saying, you know what, I need this thing now, and I don't know how much longer I'm going to need it, and I can put it on my credit card, and then I'm going to get rid of it. You're paying for the ability to do that. So think of it that way. You're paying for a capability. You're not paying for a thing. So the cloud is not, in fact, cheaper if what you're doing is hosting. But it does allow you the choice. Do you have money? Do you have time? Do you have experience? What are you actually willing to pay for? If you've got guys who rack and stack machines who are great at it, and you've got data center space, then you probably don't need EC2. You've already paid for guys who do that thing. But on the other hand, if you're an entrepreneur who has no experience with that, a lot easier to turn up an instance in the cloud than it is to build your own infrastructure. This is another one of the great myths. So, how many of you know about PUE? Power utilization efficiency. So, this notion that it gets cheaper because the data centers get greener and pack more in, that's true, but that's actually a supply side element, not a consumer side element. It's getting cheaper for the providers, right? So it's great, and it's greener, and as a matter of course, that means they'll get more machines in the data center, which just means they'll bring up more instances for you. It doesn't mean it's cheaper for you. So there's a really weird level of argument in there about power. I would say for the time being, don't pay attention to it. So I enjoyed this quote. How many of you have read Charles Stross? Yeah. So nobody ever imagined a band of orcs would steal a database. Why does that matter, other than being kind of fun? Well, mean time to failure and mean time to resolution. It's great to know when and how things fail. We've been talking about the whole conference is about how you fail at scale and what you do after, right? There's a lot of discussion about mean time to failure, about building resilient systems. But if your mean time to recover actually exceeds the value of your data, you're dead, right? What do you do about that? How many of you folks in here have contingency plans if your entire database goes down? Or corruption, or a blip in time and space. Everybody does some level of it, right? So what do you do? Believe it or not, these are not universally understood elements. So test with a production-like data set, production performance. How many of you went to Gears talk earlier? And the discussion about Tokyo and the way the performance drops at a particular point? Because if your data set is 50,000 integers, that's really simple. And anything beyond that, performance goes to 0. That's the kind of testing I'm talking about. Test with production-style data, with production kind of machines. And don't do design by laptop. These days, when it's so easy to run with these fairly high-powered laptops, so easy to run your entire platform on it, you tend to test there, and you tend to start believing your own benchmarks. And in a lot of cases, this laptop right here is a whole lot faster than an instance on EC2. in most ways that matter. And so testing on your laptop is a really bad idea. A/B testing. Folks have talked about the ability to deploy multiple versions side by side, to have cookies or to have configuration in your load balancer that allows you to say, these customers are going to the new features, these customers are going to the old features. How many of you do that? I think that is one of those differentiators, whereas as you start to grow, you're able to do that and bring new features online and testing with a percentage of customers. So you've always got that forward-moving window, and it's already in production. You just simply keep turning the percentage up, and at some point, it's 100% on the new feature. So how do you do it? You actually have to pull the plug. You actually have to be brave enough to kill something, to shut it off. First time around, if you haven't done it before, I suggest you create a test environment, looks like a production environment, and then actually do it. Run it like production. Allspaw was talking about new features go to staff first. I love that, because that allows you to do this kind of testing. What happens then if you pull the plug on that feature, or you perturb it just a little bit? Watch what happens. Watch your monitoring, see what you can do to react. Well, once you pull the plug and you watch everybody in the room scream and freak out, by the way, when you pull the plug, don't tell anybody. Just do it and see what happens. That's my favorite exercise. At Amazon, it's called Game Day. And something would just go down. It might be an entire data center. So pull the plug, watch the process, watch your people react, document the process. Have them document exactly what they did to bring it back up. And when they're done documenting, if possible, cycle through a different group of engineers and pull the plug again. Do the same thing. See if you document it adequately. So we are getting better at this. We're a startup. We're still learning. But these are the operational practices that we're building up. It's like, hey, look at that. We run a lot of CouchDB. We're those folks out on the edge like, hey, NoSQL is great. We run CouchDB on XFS, on EBS, on EC2. And I'm not even kidding. So every once in a while, things go wrong. We've got an entire process for, hey, what happens if the database goes away? And we can remount entire snapshots on new instances and bring them back up behind the internal load balancer pretty quickly now. And anybody in the group who does operations can see how that works. Okay. Oh, I wish you could see that better. I thought this was a really apt comparison because I'm a big fan of Theo. Theo and Morpheus are actually about the same level for me, so I thought this was fitting. So here's what I mean. Theo spoke yesterday about some of these elements of scale, and he talked about databases. And one of the things that's always struck me in these conversations is that tension between do you vertically scale or do you horizontally scale, as if there were only one correct answer. And clearly that's not true, but there are comparisons to be made, right? Being able to scale vertically sometimes is just a deep understanding of how that component works. This whole notion that SQL doesn't scale that came up on the panel yesterday. That's not true. It's not that SQL doesn't scale, it's that you're probably doing it wrong. And then once you've scaled it away, then maybe you need to do some partitioning or sharding or whatever. Pick your favorite technique to continue to scale, but as soon as you've done that, hey, wait, now I've got a horizontal component to what I'm doing. So it's not one or the other, right? But horizontal scale is also about availability and about reliability. It's not just performance, right? You're not trying to squeeze 99 or 99.9 out of a single unit. You're trying to squeeze that out of your entire running system. Stop thinking about machines and start thinking about complex adaptive systems. Now, another thing that Theo said the other day is that we need to be better engineers. There is science to this. There's a whole body of literature out there about it, right? So free your mind, as Morpheus would say. And since you're not Theo, and probably not Morpheus either, I would aim for John Allspaw. So there was a plug earlier today for John's book. Absolutely. This is the place you go to learn these things. Like I said, there's a burgeoning literature out there for people like us, and then there is this crest of academic literature that more and more people are getting access to. All right. A couple of definitions and then back into the design elements. So for me, this is what availability is about. For distributed systems to be continuously available, sorry, I'm reading from the slide, every request received by a non-failing node must result in a response. It doesn't mean a good response. It simply means a response. And And yeah, the pedants could say that a lack of a response is a form of response as well, but the problem is how quickly does that happen? What you want from any system that is making forward progress is it needs to tell you, I can get the data you want, or I perform the operation, or no, I can't. And apologizing is actually okay, because apologizing is a form of forward progress that protects the system. So one of the things that you can do, read globally, but write or act locally. And all this discussion about consistent data, I get it, you do. You need consistency, you need hard consistency for some things. But there are instances where it's okay to be looking at a global, temporally inconsistent state. If you've got a large system, there's a myth of temporal consistency, right? You are not seeing what's going on the other side of the planet at any given moment. The light you see from the sun is several minutes old. You are already living without consistency, right? So you look at all the data that you've got in hand, and then you want to perform an action. So a real live example of this, the system that I built at Microsoft before leaving was a bit like EC2, but it was distributed around the world. We had small points of presence by the time I left in about 15 different jurisdictions. We were in places like Kawaguchi, Japan, in Singapore, we were all over Europe, all over the US, and we had these distributed on-demand compute nodes. Now you can imagine you are not seeing a consistent state of all of those at any given point, but you may, from a central dashboard, want to take an action and say, you know what, I need 3 instances here and 5 instances here, and treat it as if it were a block. This is not going to be transactional, because this is not consistent at any time. So what do? You press the button and you say you want all these things. The actions are sent off to the local actor. So there's places where there's a coordinator running in Kawaguchi, there's a coordinator running in Singapore, there's a coordinator running in the US. The local guy has authoritative data, and he takes action and reports back. If he's not reachable, then you get an apology, you get a failure. If he is reachable and doesn't have enough capacity for you, how many people have gotten insufficient capacity responses back from EC2? How would you have felt if they said, gotcha, I'm going to give you an instance sometime? Now, don't you want it? I'm sure you hate it, but don't you want insufficient capacity as a response rather than, we'll get around to you someday when I have space? So it's the same sort of thing. And then finally, internally in your design, service level agreements between your own services. If you actually want performance, you want to understand how the system is growing and evolving, then you need to set some boundaries, even for your own services. And as you compose it in Amazon, Amazon internally was great about this, amazingly metrics driven, to the extent that one team would tell another, your service can take 100 milliseconds and no longer, or we won't render you. And every page they do is composed of a bunch of these services, and guess what? You come in late, and on the other side of the wire, and you don't get your space on the page. Smart idea. Alright, so I'm running along. I think I covered all of this. Global but inconsistent, right? And, autonomy. That's the thing. The local actors are autonomous. Now, the other reason to do this in the setting I described, globally distributed compute nodes, is that you've got smart actors of your own within that domain. You've got instances running in Kawaguchi and instances running in Singapore. And they have access to the API just like everybody else does. What if you built a system that is self-healing or self-expanding? It's like, agent running in Kawaguchi knows it needs more instances in Kawaguchi. Does it need to call back to the US to coordinate that, and then have the US call back to Kawaguchi? No. You want to act locally because that's your failure domain, right? So you want autonomous actors within their own failure domain. I think I've harped on the first part of this bad enough. What I mean by execution caching, totally different from data caching. Everybody loves data caching, it's the right thing to do and it's best. Execution caching more refers to that idea that I'm going to take your request and I'm going to keep it around. I'm going to make your intention durable, but I don't know if I can act on it yet. So I'm going to tell you I did, and then I'm going to get around to it. Because what happens at that point? Well, as a service provider, I am now responsible for holding on to that state and carrying it around for some unknown period and making good on it. And by the time the request goes back to you, I've already told you what's going to happen. I don't get another chance to come back and tell you, I'm sorry, I failed. It's a horrible contract with the consumer. Because what you've said is, I made it work, and in fact, it's a lie. It's not even a promise. So embrace that failure. Apologize. Another key point there, don't block the client. If you have to wait around to figure out if you've got the resources, then you're probably wrong. It's much better to apologize to a fast consumer and say, you know what, I don't know right now. try me back in a minute or two. Because the thing that happens if you block the client is you're blocking yourself as well. Now, if you want a high concurrency system or a low latency system, and you're blocking every client to wait to do internal processing, what happens? Well, your system doesn't scale and you can stop everybody. It's just failure across the board. So don't block the client. Corollary to that is avoid the sort of internal policy that causes you to do that. And again, ensure that the system makes progress. Anybody seen that? Who's got the new Twitter? There we go. Man, I'm jealous. It's okay to apologize, right? If something goes wrong, the system will come back. Because, I'm pretty happy about this. In the last 5 or 10 years, we've been trained. You just keep hitting refresh, right? The web is all about refresh. You're going to try again. But the weirdest thing is, so there's a difference between website design and web service design. And for some reason, folks who design web services think that those calls are precious and you can't fail and you can't apologize. Not true at all. It's the same design. You should craft smart clients and you should tell your consumers how this works. You need to apologize quickly because you need to make forward progress. An analog to that is you can get away with, in some cases, not apologizing if you've got an asynchronous design. So instead of really telling somebody, hey, I failed you completely, you give them an ID that says, you know what, I'm trying this thing, and you can check on me. Find out if I execute it for you, and my guarantee to you at some point is you will check in and I will tell you the final status. Notice that's really different from doing a callback to the client. One of them scales, one of them is manageable, and the other is not. Difficult contract. So it's better to completely fail for some of the users than to penalize all of them. Right? And how many of you know Pat Helen or know of him? There we go. So it was funny the other night, Justin Sheehy in the back, we're having a conversation, and he starts talking about this guy. He's like, he always talks about these things. He's got great analogies. I'm like, it's Pat Helen. Turns out it was. One of my favorite slides. It turns out that certain forms of async behavior look like these apologies, and to consumers, they can't tell the difference. And that's just fine. Again, trying things internally, hey, I can't do this for you, I did this for this other guy, since I did it for the other guy, how about you try again later? And your users will come back. This notion that you failed them once and they won't retry, not true. They'll come back, they'll buy it again. So how do you control it on the front end? So how many of you actually have built systems that do admission control or distributed throttling on the front end? Yeah, there are only a couple of hands. Doesn't happen often. Again, like I said, the difference between website design and web services design, more and more you see you can't quite treat them as the same thing. But the website's like, no man, I need more users. I gotta support more users. You don't want to throttle. Within reason. For these sorts of systems where you're doing lots of real work behind the scenes, sometimes admission control is exactly what you want to do. You want to keep a poorly acting consumer out there, someone who may have automated API calls against your system at a really high rate of speed. You want to stop them from damaging the entire system. That's like a DOS attack, right? You want to stop them from damaging the whole system. So what do? Well, you've most likely got a huge number of front-end machines to support load, and you've got these requests coming in, and you're trying to pick out separate the wheat from the chaff. I got this guy who's calling, he ended up over here, he ended up over here, he ended up over here, and you want to bucketize him and say, you know what, total across my whole front end, this guy gets so many calls in a minute, and then I'm going to ratchet it back. Now we only get so many, now we only get so many, now the timer is reset. So, fabulous technique for allowing the users who make it in, who are acting correctly, to make forward progress at any time while protecting the rest of your running system from the folks who are acting badly. And in web service design, especially like the thing that we're building, where we expect people to automate against it, you'll see mistakes. We've seen people we've got these Node.json documents, and you save them once in a while when configuring your machine changes. Except that we saw one customer recently in a blip of just a couple of minutes, resave the same node 2,000 times. There is no reason you need to do that. It was an accident. You need to protect your running system from those sorts of accidents. And model this. You need to know what degraded performance looks like. You need to know if everybody characterizes their system for normal behavior and possibly for complete failure behavior. Few characterize it for degraded performance and talk about what that looks like for specific customers at the time. Plug for another book, Thinking in Systems. Like I said, these are all systems theory problems, or complex adaptive systems problems. There's literature out there about sources and sinks and feedback and throttling. We're just now learning to apply these principles of organic systems to what we do as engineers. A few, I guess, lower level bullet points. Everybody is probably bored to death now of multi-version concurrency control, vector clocks, reconciliation. Everybody got that, right? Yeah, don't need to talk about that. A couple of other weird things that you'll run into with systems like this that you need to be careful of. Don't ever resurrect objects. And what I mean by that is, don't allow your system to use names for things that might be reused and used as keys to those objects. The last thing you want to do is to have some, deleted user record reused, or some other piece of data in the system that since somebody put in a new name or changed something, suddenly comes back and oh, I'm referring to that data again. Now, I've worked at Microsoft 3 different times in the last 15 years. Every time I go back, I get the same employee ID number and the same email, and every time I've gone back, strange things appear in my mail slot because they got lost the last time I worked there. I showed up the last time, and a patent cube, I don't know if you've ever seen the little Microsoft patent cubes. I showed up, and the first week I was there, a patent cube from like 5 years before appeared in my mailbox. They were just waiting for me to read. They reuse that data. So yeah, name is a property of an object. It's not its unique key, because if you refer to it again and you thought it was deleted, it just came back. So break that link, even if you don't delete it, because deleting is expensive, right? You don't want to take the time. Sunder the link between, right? If it's got some sort of unique ID, just make sure that those are always forward progressing, monotonically increasing, or randomly distributed IDs that you can't use again. All right. How many of you hate the request signing for requests to EC2 and services like that? Or maybe I should ask, how many of you like that? How many of you understand? This was actually pretty contentious. The reason that I mention it at all, we got 2 things out of doing it this way. One is that we can keep the entire system stateless. So for web service design as opposed to websites, again, there's a difference. Really nice to have your front-end boxes be completely stateless. So you can bring a brand new one up and it doesn't care about what's been going on before, and you don't have to point it at the database and hold session state or resynchronize. When you can get away with it, it's great. So that's what request signing gave us. We didn't have to control a session for authentication being logged in. We used X509 certificates because it allowed us to put public key information on these front-end machines so that the thing that was out there is not in fact exploitable. It's a piece of information everybody's already got. So instead of using a shared key approach where you're always worried about who exploits the keys for all your users, we tried to build a system where we didn't actually care about exploits against the front end, and then we hardened behind that internally. I'm not sure if this one got mentioned, but how many of you use Splunk or something like it? I love it. It's data porn. It's beautiful. The thing is, in order to really use a system like that effectively, and I don't know, somebody else may have mentioned this, you want to save everything. You really want to save everything forever. You want to keep so much of that data around, especially for a brand new service, because you don't know what you're going to need, and you don't know what you're going to want to look back on. So I've run into a number of systems that, while they save everything, they will subsample or wavelength compress or do something crazy to time series data after the fact in order to at least keep a fiction of that data around forever. Because at some point you're going to want to look back and wow, I still don't know why that thing happened. Lots and lots of literature for this. And I imagine everybody in the room understands this, but average means nothing. Average response time to the user, average number of users, average length of user in queue, average never means anything. What you really want to do is you want to build a histogram. You want to look at things like TP90, TP99. What does it look like for 90% of your users? What does it look like for 99.9% of your users? That's what you care about. And then from there, you decide which things actually need to be faster and which pieces of data are outliers. And then for the statistical pens in the room, skewness and kurtosis. What does the variance actually look like around the mean? All right. Now I managed to get it into a mode I don't understand. this is totally, what is it? It's PEBCAP, or as we said in the RA, operator headspace and timing. I don't know how to run the tool. Yeah, so like I said, there's literature out there for all of this. I don't know how many folks run sites where this sort of data actually matters to them, but if you look at something like Amazon, you want to compare day to day, or day of the week to last week, or this day of last year, and there's so much information there, statistical information, you've got confidence bands around the number of orders that you expect. So it's really cool to be tracking that in real time, all the time. To the extent that every once in a while you look at a blip and you're like, wow, hey, orders are down from what they were yesterday or last week. Then you realize it's a national holiday and everybody's simply out for the day. It's great when you've got that sort of analysis and you can do your planning. And the confidence intervals, really important. The more data you have, the more you can characterize, the better you get. I was really thrilled yesterday when Theo put engineering diagrams into his talk. Like, I'm going to do that too. I'm an electrical engineer by training, and this is what I expected to see. So this is a characteristic curve, output characteristic curve for a BJT bipolar junction transistor. The reason I put it in here wasn't just to be silly and think I'm cool. These are output curves based on differing inputs. This is what I was talking about when I said characterize the system. You don't characterize for one input, you characterize for a series of loads. So it's not just expected, and it's not just failure load. It's watching the system and characterizing it over a number of different loads. What happens? For some things, it may be a number of axes far greater than this. It might be number of users at any given time, simple concurrency. It might be which API call is being made, what is your blended workload. It may be the size of the payload in those calls, or the size of the response to those calls. All things to think about. And you don't do it for just one. You don't say, again, what is the average node data size? Like, no, what happens if somebody puts 10K instead of 1K? You find those things differ greatly. So we made a huge mistake recently at Opscode doing exactly that. We use, like a lot of people, we use Solar and Lucene. How many of you use Lucene for indexing? Yeah, fabulous tools, very, very cool. We like it and we use it and we were doing it wrong. So, order of magnitude, how many fields do you index in Lucene? 10, 15, 20, so order of magnitude, 10, right? Less than 100. We got to the point where we didn't realize what we were doing is a power set expansion of this hierarchical JSON, and that in that power set expansion, there were unique pieces of keys unique to every host that was saving itself. So by the time we had a considerable number of customers on the platform, we had 800,000 unique indexable fields. So that graph at the bottom, that's a graph of rising commit times in Solar, and it's in hundreds of seconds. Yeah, we were doing it wrong. When you get to 1,000 seconds committing in Solar, you're pretty sure that you're going straight to hell. The really cool thing, though, after the complete meltdown in there, the gap in time, is we got it right. So that shows the point where we characterized the curve like, hey, they benchmarked like 30 fields. And we figured out how many fields we had. So step one, we figured out how many fields we had, and that was the axis that was actually variables. So the first drop off there is a deployment where we fixed the first half of the problem. And you notice that it starts rising again, never gets to the magnitude it was before, and we made a couple of other discoveries. And you see that blip at the other end. So we're monitoring this all the time, and now we've got it under control. And it's actually quite fast again, which is what everybody wants. But the point of the story is we were doing it really wrong because we had not characterized how that service changes. And we didn't know that really that was the axis that we were sensitive to. And then also, there's always periodicity to these sorts of things, or quite often. So you can see that the response time is not a lot of variance, except there's this one time. It's like, oh, hey, we've got a customer, like I said, who commits 2,000 nodes right now. What does that do to the system? So it's another one of those things that you need to characterize. I'm going to skip just a little bit here. I'm going to get a little short on time. Back to this thing about consistency and also the notion of globally inconsistent local actors. So we've got, and I suspect a lot of folks like this, we've got two calls that look a lot alike inside of the Opscode platform. One is this thing is authorized. It runs through our auth system. It says, is this actor actually authorized to perform this operation on this object? And quite often what that means is he is authorized to do it because he is inside of a particular group. We've got role-based access control that we built in-house. Maybe I shouldn't have been in that part. We've got role-based access control. And so we ask this question a lot. Is authorized? Every operation is authorized. It's got to be fast. So what we're doing is a lookup, and sometimes that comes out to be, is this actor in this group? Totally different operation from list me all of the actors in a group, right? Is authorized has to be authoritative and correct all the time for every operation. So we actually perform that differently than the list group, which is a consultative operation. It is possibly inconsistent, because you know what? We haven't gotten back to update that yet. That's the thing that most often you're looking at in the UI, and after the fact, for analytics. You know, who are the guys in this group? You expect to see it become consistent at some point. It can't be out for very long, but it's not the fast path. It's not the thing you're asking the questions against all the time. I keep mentioning this whole thing about failure domains. Wow. And there's gray on that slide that simply does not show up at all. We were really concerned building EC2 about the size of a failure domain. Okay, you have to decide, and this goes directly to which operations you perform at what level. We wanted to drive, as you do in most distributed systems, autonomy and decision-making all the way out to the edge where it scales. So we actually had multiple failure domains. A single machine, a DOM0 and several DOM-Us, is a failure domain for one sort of case. It's a failure domain, for instance, for IP address allocation and for instance metadata, because that's where those things live. We did not want to have to call back to a centralized source for something like address allocation, because if we did, and the centralized source went away, the entire fleet stops. But if certain machines stop, you're simply unable to allocate instances there, and everyone else, again, makes forward progress. Our DNS was the same way. We did some really, sort of fake Anycast style tricks to have DNS servers in every rack, because we didn't want to be concerned about the traffic between them should something fail. And we also wanted the ability to bring up new DNS servers at any time inside the rack. Like, well, hey, load those here. We're not going to bring up ones globally that cause us to shun more traffic somewhere else. We're just going to bring them up inside of the failure domain, isolate the traffic there so that they don't affect others. And the thing that I mentioned building in Microsoft, these coordinators, same sort of thing. I mentioned the zones. If you're in Kawaguchi, you don't affect Miami, and vice versa. Okay, everybody still awake? All right. Anybody need to get up and stretch for a minute? I got like 7 minutes left. I want to answer some questions. So, all right, last two slides I'm going to do. So what things went right? What things would I consider success in the designs for things like EC2? The shareable engine. The ability to give your work out to a friend, have them tinker, rebundle, add to it, and hand it back out. How many of you run services in EC2 based on the AMI work of others? Yeah, that's the way it's supposed to be. You shouldn't have to do all the work. It's all shareable. The metadata, I mentioned that. Open API. So eucalyptus wouldn't exist without something like that. Now, there's some disagreement about what open actually means in this context. As I mentioned, primitives, this notion that you compose how you want and leave the policy to others. Pay-as-you-go resources. You wouldn't be able to start these small concerns and watch them grow if they couldn't do this on-demand and pay-as-you-go. And then free traffic between S3 and EC2. How many of you are EC2 customers and serious S3 customers as well? Yeah, all of the data that we shuttle back and forth. You could probably move someplace other than EC2 for your compute, but what would you do for your storage? How would you get all your data out of S3? Okay, so what went wrong? Well, it turns out soap makes little girls cry. It makes me cry. Maybe I'm a little girl. I'm so sorry. The front end API, the SOAP API, is entirely my fault. I have a defense for it. I was boxed into a corner. I had an entire REST API written, but the middleware was chosen for us. So it is. Even before I left, 75% of the traffic, and I think it's higher now, going to the services was through the query form of the API, not SOAP. I don't know anyone at this point who would defend SOAP, other than perhaps if you're building .NET services that only talk to each other, or it's extremely simple tools. And perhaps Java services the same. EC2, in some ways, is still way too hard to use. In some sense, it is too primitive, right? And related to that, it's still a commodity business, or rather it's becoming a commodity business. It's driving the price point to the bottom. And what happens at that point? Things like quality become questionable. You want to run it cheaper and cheaper, and it is just this compute service, right? So it only gives you so much in terms of its depth, and you need to compose on top of that. All the tools aren't quite there yet, and at the same time there's competition for who's going to reach the bottom in price first. Also, I said API always and UI afterwards. We went too long. The UIs were really bad for EC2, and it made adoption much slower. Fortunately, it built an ecosystem. How many of you use RightScale? Or something like it? Anybody? So other people did step in. There's an ecosystem for it, but we're relearning that same lesson at OpsCo. You do really want a good UI, something that's useful. There we go. So where are we going? At that point, I'm going to open it to you. Questions if you've got them. Thank you very much. Questions? Did I lose it? There. Any questions? Or is it post-lunch nap time?
How does when you were hands-on, how did they decide which direction the service would go? How they could develop a lesson driven or?
Yeah, good question. So the question is, at Amazon, when I was there at the time, was the design of the API customer-driven? How did we come to the decisions? We really, by virtue of what we were doing, were making it up as we went along. The only input we got is there was a sort of a centralized committee that was trying to build some standards on what was supportable and what was debuggable, which is in some sense where this middleware came from that I was talking about. But we were winging. If you notice, there are things in the API that their intent is not quite clear, like the reservation ID. But only now, when we're seeing things like spot instances and building a market on instances, are some of the rationale behind these missing pieces coming out. So that we were winging. Other questions? Yes?
On your last slide, you had infrastructure as a service, and I think you were kind of alluding to there's something more to come. Do you see that people are kind of getting a little dissatisfied or moving beyond infrastructure as a service? Where are people going to now? Where's the real stuff?
Right. So the question is infrastructure as a service just not enough at this point? And what is the next step and where are we going? I think you're right. And there's a problem in that it's the right primitive for what it does, but you need more than just that. And at one side of the spectrum is EC2, and it doesn't give you much other than just raw compute. And at the other side are things like Microsoft Azure that want to do everything for you in sort of one way. And there's really no middle ground. So those who say, well, that one way is not my way, this other thing is not enough. So yeah, there needs to be something in the middle. Unclear where that's going to end up. There are those who want to standardize those things. There are computing units, and there are storage units, and there are database units. And frankly, I don't believe in that form of standardization. Hasn't worked so well. Hasn't been necessary so well. Yes?
Internally, do you utilize the EC2 service for like monitoring hosts and things like that, or would you set up, basically set up on bare metal for that kind of thing?
Yeah, great question. So would you monitor, in effect, would you monitor EC2 from inside of EC2, or would you monitor it from outside? Both. Absolutely. So Ops code is deployed on EC2 now, and we do monitoring from the outside, and we do instance monitoring from the inside. You want to see what's happening for customers who are outside of that boundary. And there are instances as well, just for our own service monitoring, where we can see things from the outside because of partitioning or whatever that we don't see from the inside. So yeah, it's not enough. It's a bit like the telcos with signaling system 7. You want something outside, you don't want it to be in-band just your voice signals. All right, going once, going twice. All right, thanks again. I appreciate it.